Okay, chapter 25 is on electromagnetic induction. So what is that? Well, it turns out when you take a magnet, like a regular bar magnet, and you plunge it into a coil of wire, this can generate an electric current. This was first discovered sort of simultaneously by Faraday and Henry on opposite sides of the Atlantic in 1831. And so you can do this in one of two ways. You can either move a magnet with a magnetic field perpendicular to a wire, and that will generate a current, or you can move the wire within the magnetic field. Either way, it's something to do with the motion and this magnetic field. It generates an electric current. So if you have multiple loops in a coil, the more loops you have, the greater the voltage you produce for the same speed of motion of the magnet. And when you push a magnet into a coil, it will induce a current, and that current in a coil makes an electromagnet, and the effect of that magnet is to push away the motion of the magnet that's attached to your hand. So basically, the more coils that are there, the more work you do. So you're generating this voltage and you're generating some electricity, but you're doing work in order to generate that electricity by pushing two magnets against each other. So Faraday came up with a law to describe this, which is that the induced voltage in a coil is proportional to the number of loops multiplied by the rate at which the magnetic field changes within those loops. And then that voltage produces a current, which depends on the resistance of the coil, the circuit that's connected to it, and how much voltage is produced. So voltage is induced in a wire by changing the magnetic field that passes through some loops of wire or a coil. This can be done by moving the loop near the magnet or moving the magnet near the loop. In a guitar pickup, each pickup has a little coil with a magnet in it. The magnet magnetizes the steel strings in your guitar, and then as that magnet moves by the coil, it generates an electric signal. You can also change the current in a nearby loop, which then changes the magnetic field passing through your loop and creates a magnetic field, or creates an electric current. Some applications. If a car moves over some underground coils of wire, this can trigger traffic lights. The metal detectors in airports work by altering the magnetic fields in coils as somebody walks through with metal in their pockets. The magnetic strips in the back of credit cards, as you push them rapidly through a sensor, that can create electric current. Recordings of sound on magnetic tape work by Faraday's law, and any electronic devices like iPods or computers will store memory on their hard drives using Faraday's law as well. So an electric generator is the opposite of a motor. You're taking mechanical input, you're rotating a loop of wire in a stationary magnetic field, and that produces an alternating voltage, which then can be used to create electrical current output. So the frequency of this voltage changes or is set by the frequency that you rotate the loop in a magnetic field. So these dashed lines represent a magnetic field. It's maximum going through the loop here, and here the loop is perpendicular to or parallel to the field, so there's no field passing through it. Here the loop is reversed. And so you see as this loop goes round and round, the voltage goes up and down in time. And so using this theory of electromagnetic induction, people like Tesla and Westinghouse showed that with steam engines you could generate sufficient amount of electricity to power entire cities. This is how electricity became popular in the early 20th century. These days, a lot of power production is done with magnetohydrodynamic generators, MHD. which take away a turbine or any moving parts and just push high-speed plasma through a magnetic field. The plasma has charged particles in it, which then separate out onto the plates of a parallel plate capacitor, and this generates, now it's actually a DC voltage, which can also generate electric current and power. A transformer in electricity is when you have two coils, sometimes both of them wrapped around some piece of iron, and you have an input coming from some AC voltage source, so alternating current voltage source goes through a primary coil. That induces a magnetic field which is changing, going through the secondary coil, and then that produces an output voltage. A step-up transformer is one that produces a greater voltage in the output than in the input. And it's done by increasing the number of coils. So, for example, here's 1 volt input AC in this side of a transformer. On the other side, you have 2 loops, or 2 turns in the coil, and this produces 2 volts output. So that's a step-up transformer. And a step-down transformer has fewer turns in the output coil than in the input coil, and so it produces a smaller voltage. So here's the relationship. Primary voltage divided by the number of turns in the primary equals the secondary voltage divided by the number of turns in the secondary. If you see these tin cans on telephone poles in your neighborhood, those are step-down transformers. The input comes in at about 2400 volts. This steps it down by a factor of 10 to 240 volts for distribution to your houses. So the rate of energy transfer is called power, and it turns out that the power into the primary equals or is slightly greater than the power output of the secondary. Or if you neglect the little heat losses that happen here, the voltage times the current in the primary equals the voltage times the current in the secondary. So if you step up the voltage, you're stepping down the current. And that's how power transmission works. Almost all electrical energy sold these days is in the form of AC because of the ease with which it can be transformed from one voltage to another. Large currents in wires produce heat and energy losses. So if you want to transmit power over great distances, it's best to use high voltages and low currents. So normally here might be Niagara Falls producing power at maybe 25,000 volts. You can use step-up transformers to transform this up to like 750,000 volts for long distance transmission to the Toronto, and then you step down that voltage again to 440, 240, or even 120 volts to distribute it to houses where it will be more safe. And lastly, electromagnetic induction is a two-way street. Faraday's law states that you create an electric field and an electric current when you change a magnetic field with time. Maxwell's counterpart to Faraday's law is that if you change a magnetic field, that a magnetic field is induced when you change the electric field with time. So a changing magnetic field induces an electric field, and a changing electric field induces a magnetic field. So these two things play off one another, and if you look at these red lines as being a changing electric field and the blue lines as being a changing magnetic field, the two things produce one another and can produce a wave in the electric and magnetic fields. And this we'll find is what light is. Light and radio waves, X-rays, all of these things are waves in the electric and magnetic field that we'll study in the next chapter.